Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll study classification functions in scikit-learn. In this week, we'll study sklearn functionality for implementing classification algorithms. We'll cover sklearn APIs for specific classification algorithms like least square classification, Perceptron, and Logistic Regression classifier. We'll study these algorithms with regularization, and we'll also study how to extend these algorithms to multi-class, multi-label, and multi-output settings. We'll also cover sklearn APIs for different classification metrics. Cross-validation and hyperparameter search for classification works exactly like how it works in regression setting. However, there are a couple of cross-validation strategies that are specific to classification. And we'll study those cross-validation strategies in this slide deck. In this video, we'll cover sklearn APIs for classification. There are broadly two types of APIs based on their functionality. One is generic and second is specific. SGDClassifier is an example of a generic API, whereas there are specific APIs for logistic regression, Perceptron, and Ridge Classifier, which is used for implementing least square classification. There are also specific APIs available for k-nearest neighbor, support vector machines, and naive-based classifiers, which will be studied in later weeks. In case of generic APIs, we use stochastic gradient descent for optimization, whereas in specific APIs, we use specialized solvers for optimization. The generic API is customized to specific APIs by specifying the loss function, and we'll see exactly how this is done later in this video. All sklearn estimators for classification implement a few common methods for model training, prediction, and evaluation. Model training is done through the fit method that takes feature matrix and label as inputs, along with some other optional arguments. Then there are a couple of methods for prediction. One is predict, that takes feature matrix as an input and predicts class labels for the samples. And then there is decision underscore function, which also takes feature matrix as an input and predicts confidence score for samples. Then there is a score method for evaluating the classifier that takes feature matrix and label as input, and there is an optional argument about sample weight. Score returns mean accuracy on the given test set and labels. There are a few common miscellaneous methods like getParams that gets the parameter for the estimator, setParams that sets the parameter of the estimator, then densify that converts coefficient matrix to dense array format, and sparsify which converts coefficient matrix to sparse format. Now let's study how to implement different classifiers with sklearn APIs. Let's start with implementation of least square classification with Ridge Classifier API. Ridge Classifier is a classifier variant of the Ridge regressor. It can be used in binary and multi-class classification. In case of binary classification, it first converts the binary target to -1 and +1 and then treats the problem as a regression task. It optimizes the objective of the regressor. So the Ridge classifier minimizes a penalized residual sum of squares. So this is the predicted label, this is the actual label, and we take square of the difference and we penalize it by, let's say, the second norm of the weight vector, which is scaled by alpha, which is the regularization rate, and we find out the weight vector W, which minimizes the whole expression. So Sklearn provides different solvers for this optimization. The predicted class corresponds to the sign of regressor's prediction. So if regressor predicts a negative value, the predicted class would be -1, and if the regressor predicts a positive value, the predicted class would be +1. Ridge classifier can also be applied in multiclass classification. It treats the multiclass classification problem as a multi-output regression problem. The predicted class corresponds to the output with the highest value. Let's see how to train a least square classifier. We first instantiate a classification estimator without passing any arguments to it, which creates a basic Ridge classifier object without any customization. This uses all the default parameters. So Ridge classifier can be imported from sklearn.linear_module. So we have Ridge classifier object created in the second line. Then we call the fit method on the Ridge classifier object with training feature matrix and label vector as arguments. Again, in case of binary classification, it will be a label vector, but in case of multi-class classification, it will be a label matrix. So we simply call the fit on the Ridge classifier object by passing the feature matrix x_train and label vector or matrix, which is y_train. So the model is fitted with, or we learn the parameters of the model by looking at the feature matrix and the labels supplied as part of the training. Let's see how to set regularization rate in Sklearn. So we use alpha to control the regularization rate. We need to set alpha to a float value, and the default value for alpha is 0.1. Alpha should be positive, and larger value of alpha specifies stronger regularization. So we simply set the value of alpha in the Ridge classifier constructor by setting the desired value for controlling the regularization rate. Let's see what are the options available to us for solving the optimization problem in Ridge classification. We can use one of the 7 solvers that are out here: SVD, Cholesky, sparse, CG, which is conjugate gradient, LSQR, SAG or SAGA, and LBFGS. SVD uses a singular value decomposition of the feature matrix to compute the Ridge coefficients. Cholesky uses the SciPy linear algebra solve function to obtain a closed form solution. Sparse CG uses conjugate gradient solver of scipy.sparse.linal.cg. LSQR uses dedicated regularized least square routine, and LSQR is the fastest solver. SAG and SAGA uses stochastic average gradient descent iterative procedure. SAGA is unbiased and more flexible version of SAG. LBFGS uses LBFGS implementation from SciPy. It can be used only when coefficients are forced to be positive. We can specify different solvers depending on the problem at hand. For large-scale data, we use sparse underscore CG solver. When both number of samples and number of features are large, we use SAG or SAGA solver. The fast convergence is only guaranteed when features are approximately on the same scale. So there is a facility where we can make Ridge Classifier select the solver automatically. So we have to set the solver argument to auto in the Ridge Classifier constructor. And auto chooses solver automatically based on the type of the data. So the default choice for solver is always auto. Is intercept estimation necessary for Ridge Classifier? This could be one of the questions that might come to your mind. So if the data is already centered, the intercept estimation is not necessary. In that case, we set fit underscore intercept argument in the constructor to false. By default, the fit underscore intercept argument is true, so we have to set it to false in case we do not want Ridge Classifier to perform estimation computation. Let's see how to make prediction on the new data. We use predict method to predict class labels for samples. We first arrange the data for prediction in a feature matrix of the shape number of samples, number of features, or in sparse matrix format. And then we call the predict method on classifier object with feature matrix as an argument. So we already had created a Ridge Classifier object. We simply call the predict method on that by passing the feature matrix, and we get the class labels as an output. So other classifiers also use the same predict method. So there is another variant of Ridge Classifier, which is Ridge Classifier CV, that implements Ridge Classifier with built-in cross-validation. Now let's implement Perceptron classifier with Perceptron API. Perceptron classification is the simplest classification algorithm that is suitable for large-scale learning. It shares the same underlying implementation with SGDClassifier. So we can also implement Perceptron with SGDClassifier by setting the loss to Perceptron, setting the initial value of the learning rate to 1, and learning rate equal to constant, and without setting any penalty. Perceptron uses SGD for training. So these two definitions, or these two instantiations are equivalent. We can either use Perceptron or we can use SGDClassifier with this particular parameterization, where we are setting loss to Perceptron, initial learning rate to 1, learning rate scheduled to constant, and penalty to none. Then this SGDClassifier instance would train a Perceptron model. So we can implement a Perceptron classifier by first importing Perceptron from Sklearn.linear module, and then we instantiate a Perceptron classifier. Then we call the fit method on the Perceptron estimator object with training feature matrix and labels as argument. And this is very similar to what we did in Ridge Classifier. So Perceptron can be further customized with the following parameters. We can set penalty to, let's say, L2 or L1. We can also set L1 ratio in case of elastic net penalty. We can set the regularization rate alpha. We can also set the early stopping criteria. We can also control whether we want to fit the intercept. We can specify the max iteration. We can also specify number of iterations with no change in order to set the early stopping criteria. And then we can also set tolerance, then initial learning rate and validation fraction. So you may recall that most of these arguments are very similar to what arguments you used in SGD regressor during linear regression module. So perceptron classifier can also be trained in an iterative manner with partial fit method. Perceptron classifier can be initialized to the weights of the previous run by specifying warm start equal to true in the constructor. So these two features help us to use perceptron classifier in large-scale learning. Let us implement logistic regression classifier with logistic regression API. Logistic regression API implements logistic regression classifier, and logistic regression classifier is also known by different names. There are names like logit regression, maximum entropy classifier or maxent, and log linear classifier. All of them refer to logistic regression. Logistic regression API basically optimizes the following expression. So it tries to find out the value of W and C that minimizes the regularization penalty plus C times the cross entropy loss. So this expression is slightly different than what we studied in machine learning techniques course about the logistic regression. Instead of applying lambda, which is regularization rate, to the regularization penalty, it instead applies C, or it instead scales the cross entropy loss. So this C over here is inverse of lambda, or the regularization rate. So this particular logistic regression API can implement binary classification. Then it can also does multi-class classification with one versus stressed setting, and it can also implement multinomial logistic regression. It also has provision for L1, L2 and elastic net regularization. So how do we train a logistic regression classifier? We first instantiate a classification estimator without passing any arguments, which creates a basic logistic regression classifier object. Then we call the fit method with training feature matrix and label as argument. So that helps us to train the logistic regression classifier. So logistic regression uses specific algorithms for solving the optimization problem in the training. These algorithms are known as solvers. The choice of solvers depends on the classification problem setup. It depends on the size of dataset, number of features, and labels. Let's look at different solver options for logistic regression classifier. There are 5 different solvers that we can use, namely Newton CG, LBFGS, LibLinear, SAG, and SAGA. These are basically different optimization algorithms. And as part of practice course, you need to use how to use these solvers and also find out what are the suitable situations for using these solvers. You're not expected to know the details of the optimization procedures behind each of these solvers. So for a small dataset, LibLinear is a good choice, whereas SAG and SAGA are faster for large datasets. For unscaled dataset, LibLinear, LBFGS, or Newton CG are robust. And remember that SAG and SAGA uses stochastic gradient descent, which is sensitive to the feature scaling, and hence they are not suitable for unscaled datasets. If you want to solve the multi-class classification problem with multinomial loss, then LibLinear doesn't support that case. So in order to use multinomial loss, you have to use Newton CG, LBFGS, SAG or SAGA as the solvers. LibLinear solver only supports the 1 versus race scheme for multi-class classification. By default, logistic regression uses LBFGS solver, and you can specify the solver, the desired solver in the constructor of the logistic regression object. So let's see how to add regularization in logistic regression classifier. Logistic regression supports L1, L2 and elastic net penalties. And if you do not want to use any regularization, we'll have to set the penalty to none. So regularization is applied by default because it improves the numerical stability. By default, logistic regression classifier uses L2 penalty, and we can change this penalty to the desired penalty by setting the penalty argument in the constructor of logistic regression classifier. Again, note that not all solvers supports all penalties. You have to select appropriate solver for the desired penalty. So L2 penalty is supported by all solvers, whereas L1 penalty is supported only by a few solvers. So we can see that L1 penalty is supported only by LibLinear and SAGA. So elastic net penalty is only supported by SAGA. So if you want to use elastic net penalty, then you have to use SAGA. If you want to use L1 penalty, then you have to use either LibLinear or SAGA as solvers. For L2, you can use any of the solvers. All the solvers support L2 penalty. Let's check out how to control the amount of regularization in logistic regression. So as said earlier, the regularization is controlled via parameter C, which is inverse of regularization rate. So recall that logistic regression optimizes the following equation, which is regularization penalty plus C times the cross entropy loss. It finds out W and C that minimizes this particular expression. So the value of C is specified in the constructor and it must be positive. The smaller value of C leads to stronger regularization, whereas larger value of C leads to weaker regularization. And remember that C is inverse of regularization rate. That's why strong value means strong. That's why small value means stronger regularization and large value means weaker regularization. So logistic regression classifier also has class underscore weight parameter in its constructor. So what purpose does it serve? So class underscore weight parameter helps us to handle class imbalance with differential class weights. So the mistakes in a class are penalized by the class weight. Higher value would mean higher emphasis on the class. This parameter is also available in other classifiers in Sklearn. So this is one way in which we can handle the class imbalance problem. In earlier weeks, we have also seen a couple of other ways to handle class imbalance, either through sampling and through specialized method like SMART. So there is a very interesting Stack Overflow discussion on this parameter, and I would recommend you to read this discussion to understand the significance of this parameter in a better manner. So there is another variation of logistic regression, which is logistic regression CV, that implements logistic regression with built-in cross-validation support. It helps us to find the best value of C and L1 ratio parameters according to specified scoring attribute. We'll look at logistic regression CV in greater detail later in the model selection. So now, up until this point, what we did is we basically looked at specific classifiers for least square classification, for logistic regression, and for perceptron. We can also implement these classifiers with a generic SGD classifier API. And in order to implement a specific classifier, we need to set the loss parameter of the SGD classifier appropriately. Let's study SGD classifier API. SGD classifier uses SGD as an optimization technique. SGD is a simple yet very efficient approach to fitting linear classifiers under convex loss functions. So we can use this API to build a variety of linear classifiers by adjusting the loss parameters. SGD classifier easily scales up to large scale problems. Problems with more than 10 raised to 5 training examples and 10 raised to 5 features can be easily handled with SGD classifier. It also works with sparse learning problems. It is useful for text classification and natural language processing. It also supports multiclass classification by combining multiple binary classifiers in one versus all schemes. So the way we can customize the SGD classifier is by setting the appropriate loss functions. Let's look at different loss parameters or different options for loss parameters. We can use hinge loss, log loss, modified Huber loss, squared hinge loss, perceptron loss, and squared error loss. The hinge loss is used for linear support vector machine. The log loss, when we set the loss to log, we are effectively training a logistic regression model. When we set the loss to modified Huber loss, we get smooth hinge loss that is tolerant to outliers, as well as it gets us probability estimates in case of linear support vector machines. So squared hinge loss is just like hinge loss, but it is quadratically penalized. Perceptron loss, when we set loss parameter to perceptron, we are effectively training the perceptron algorithm. When we set the loss to either squared error, Huber loss, epsilon insensitive loss, or squared epsilon insensitive loss, we are basically using the SGD classifier to train the least square classification. So these are all the losses that are used in regression, and when we set the loss to one of these losses, we are effectively training the least square classification. By default, SGD classifier uses hinge loss, and hence it trains linear support vector machine classifier. Again, in other words, an instance of SGD classifier might have an equivalent estimator in Sklearn API. For example, when we set the loss to log, it is equivalent to logistic regression API with solver equal to SGD. When we set SGD classifier loss to hinge, we basically get linear support vector machine. Let's see how SGD classifier works. So SGD classifier implements a stochastic gradient descent procedure. The gradient of the loss is estimated with one sample at a time, and the model is updated along the way with decreasing learning rate. SGD classifier is efficient and it is easy to implement. On the flip side, it has a number of hyperparameters that we need to tune in order to get it working. And SGD classifier is also sensitive to feature scaling. So it is important to shuffle the training data before fitting the model, and it is also important to standardize the features because SGD classifier works well with standardized features, or when all the features are on the same scale. So we can instantiate SGD classifier estimator by setting appropriate loss parameter to define the classifier of interest. By default, it uses hinge loss that is used to train linear support vector machine model. If we want to use SGD classifier to train, let's say, logistic regression, we have to set the loss to log, and the log loss defines a logistic regression classifier. We call the fit method on SGD classifier object just like any other classification, just like any other classifier estimators. We send the training feature matrix and label vectors, label vector or matrix as arguments. We can also perform regularization in SGD classifier. We can use either L2, L1 or elastic net regularization. We have already seen elastic net regularization while we were studying linear regression module. So in case of elastic net regularization, L1 ratio controls the convex combination of L1 and L2 penalty. The default value of L1 ratio is 0.15. So by default, SGD classifier uses L2 penalty. We can control the amount of penalty through parameter alpha. And alpha is a float value and the default is 10 raised to minus 4. Let's see how to set the maximum number of epochs for SGD classifier. Just like in SGD regressor, we can use max iter parameter here. The default number of iterations are 1000. We can set max iter to any number of iterations that we desire the SGD classifier to train. There are some parameters that are common between SGD classifier and regressor. There are parameters like learning rate, then average SGD, warm start, and stopping criteria. These parameters are exactly like how we used in SGD regressor. If you want to know more about these parameters, I would recommend you to have a relook at the SGD regressor video in the linear regression module. We can set the learning rate to constant, optimal, inverse scaling, or adaptive. We can also set the average parameter to true or false that helps us to inform the SGD classifier whether we want to use average SGD. We can set warm start to true or false. Warm start helps us to initialize SGD with the parameters learned in the previous iteration. And there are a bunch of parameters that helps us to specify the stopping criteria. The parameters like tolerance, n underscore iter underscore no underscore change, max iter, early stopping, and validation fraction. All these parameters help us to specify the stopping criteria. In this video, we learned how to implement different classifiers with Sklearn APIs. We learned how to implement least square classifier, Perceptron classifier, and logistic regression classifier with specific APIs like Ridge Classifier, Perceptron, and logistic regression. We can also implement these classifiers with a generic SGD classifier by appropriately setting the loss parameter. For example, we can implement a logistic regression classification model with the loss equal to log. We can implement Perceptron classifier by setting the loss equal to Perceptron, and we can learn least square classification model by setting the loss to squared underscore error. We also learned that classification estimators implement a few common methods. These estimators can also be readily used in multiclass setting. They support regularized loss function optimization. And finally, all classification estimators have the ability to deal with class imbalance through class underscore weight parameter in the constructor. In the next video, we'll implement or we'll extend these estimators in multiclass setting. So now you know how to implement different classifiers with Sklearn APIs.